All right, our transformations do not ever go away, unfortunately for some of you, as you have not enjoyed them very much. But hopefully they're becoming more clear. So here we're looking at transformations with our exponential functions. We're going to start with the basic function 3 to the x, and then we're going to do some transformations. So in order to do that, I want to start with actually graphing that basic function of 3 to the x. We're going to do this by hand. I want you to really understand what this exponential function means and how it works. So we're going to start by doing it by hand. So I'm going to graph it on the first graph so we have it to refer to as we do all of our transformations. 3 to the x. Let's just pick some nice values of x. If I pick 0, 3 to the 0 is 1. And apparently it's not going to work. Let's try this one. There we go. All right, and then we have 3 to the first power. 3 to the first power is 3. 3 squared, so when x is 2, is 9. Okay, we see a couple points on our graph. Now let's go ahead and get some negatives. 3 to the negative 1, it's 1 over 3 to the first, or 1/3. 3 to the negative 2 is 1 over 3 squared, which is 1/9. Okay, we'd have 1/27th, 1/81st. They get really small. Think about powers of 3. Is there any way for 3 to a power, if powers just mean repeated multiplication or negative powers mean repeated division? Is there any way to get a negative when you have a base value of 3? Okay, if we keep going smaller and smaller, hopefully we start to see that and understand that that's getting closer and closer to 0, 1/81st, 1 something larger than that. Okay, we get these really tiny values here as we go to the left. As we go to the right, 3 cubed is 27. I'm way off my graph. Okay, but nothing will ever make 3 to a power become negative. So I have the function coming right along the x-axis here and then curving relatively quickly upwards. By the time I got to 3, I'd need to be all the way up to 27. Okay, so this is our basic shape to our function. It has a curvature that looks like this for pretty much all of our exponential functions. Now we're going to look at our transformations. Okay, let's look and see what we have. 3 to the x minus 2. Okay, there's something changed in the x value, in the exponent with the x. There's a minus 2. When it's applied to the x, think for a moment, does that mean it has a horizontal change or a vertical change? Hopefully you're recalling that that's horizontal because it's applied to the x. A minus 2 and everything horizontal works backwards, so that minus 2 moves me right 2 units. So my new function is this whole original function moved to the right 2 units. So this point that was at 0 is now at 2. This point that was over 1 is now over 3. Okay, this point that was over 2 is now over 5. Oops, 4, because we're only moving 2. Okay, here the one that was at 1/3 over 2 units, 1/9 over here, and we get the same shape to our graph, just slid, maybe that's the right way to say it, slid over 2 units to the right. Okay, it continues forever that way. Okay, so we had that transformation of moving to the right. Okay, well, here we have 3 to the negative x. Okay, again applied to the x, so it's a horizontal change. A negative does a reflection, so a horizontal reflection has to go sideways, so we're going over the y-axis. So this is a reflection over the y-axis. And looking back again at this blue graph, we have a reflection over the y-axis is not going to change anything that's on the y, so that point at 0 is still up at 1. This point that's over 1 up 3 is going to reflect over, so it's going to be back 1 and up 3. This point that's over 2 and up 9 is going to be back 2 and up 9. Let's think about those for a moment. If I actually put -1 in for x, I have a -1, which makes it +1, and 3 to the first is 3. Putting -2 in, -2 makes that a +2, and so that's 3 squared, which is 9. Okay, we do get, when I put in -2, a y value of 9. Okay, if I have 1, if I look at this point over here at -1, when that reflects over the x-axis, it moves to the right to +1. That was at 1/3. Then we have 1/9, and everything tinier after that. And so we get this reflected graph that looks like this. Okay, now we have another type of change. We're multiplying 2 times the whole 3 to the x, 2 times the whole function 3 to the x. Okay, applied to the whole function is a vertical change. Vertical changes are exactly like we expected. This is a vertical stretch by 2. 2 times 3 to the x. So again, back to the original blue graph here. On the x-axis, we were up at 1. Vertical stretch makes that move up to 2. When x was 1, we're up at 3. Multiplying that by 2 for the vertical piece takes that point that's up at 3 and moves it up to 6. Okay. For over 2, we were up at 9. Multiplying that by 2 put me up at 18, so I'm clearly off my graph. Going in the negatives, when I had -1, I was up at 1/3. Multiplying that by 2, I'm up at 2/3. Then when I was over at -2, I was at 1/9. Multiplying that by 2 is 2/9. And again, I'm now still seeing that curve to the graph. And I'm going to have the graph come right there along the x-axis. Okay, we see that we have that vertical stretch. Okay, it's not quite as easy to see on this, as the shape looks very similar. It's just got a sharper turn here. Okay, so we have the transformations to pay attention to as we think about our exponential functions. If the whole graph is shifted up or down, this horizontal line, which ultimately is an asymptote, we do have a horizontal asymptote on these. For all of these, it starts at y equals 0. Okay, it doesn't cross that line at y equals 0. Y equals 0, and here, all of these are y equals 0. The only way that horizontal asymptote changes is if there is a vertical shift. If I shift this whole graph up 2, then my horizontal asymptote would be at y equals 2. Okay, if I shift it down, obviously, the horizontal asymptote would go down as well. All right, so you'll have a chance to practice those a little bit more in your homework. Exponential growth and decay is really one of the biggest applications of our exponential functions. We do see a lot of things that grow exponentially, at least for a period of time. Okay, and so we need to identify the difference between growth and decay. This growth, as you'd expect, means increasing, growing, getting larger. Decay would be a decreasing function. If I have my basic function, f of x equals a times b to the x, we need to think about what determines whether the values of the function are getting bigger or if they're getting smaller. Okay, we have a couple graphs above to take a look at as we think through that. Here, my original blue graph, the basic function of 3 to the x, I see that as the x values get bigger, the y values also get bigger. That is the idea of growth. So basic 3 to the x had a growth. Okay? If I shifted it right or left, it continued to be a growth function. Here, I see it decreasing. As I go to the right, as I have bigger and bigger x values, my y values are getting smaller. This would be a graph or a function that's considered a decay function. Okay, back over here, we have growth again. Okay, the key to determine growth versus decay is really nothing changed here about the a value. The a value is 1 for both of those. What changed is really the base. We don't see it here. They both look like a base of 3, but notice the negative. Really, that base is 1/3 because of that negative exponents. If we pay attention to our base, that determines whether we're growth or decay. If my base is bigger than 1, okay, so I have something like the 3 or maybe 2 or maybe even 1.1. If I take that and put larger and larger exponents on it, say 2, 2 to the first is 2, 2 to the second is 4. Anything bigger than 1, if I put larger exponents and larger exponents, I get a larger function value. So greater than 1 is going to give me growth. If my base is less than 1, okay, this one technically has a base of 1/3. If my base is 1/3 and I do 1/3 to the first power, I get 1/3. 1/3 squared gives me 1/9, smaller. 1/3 cubed gives me 1/27. Okay, if I work in the negative world, we see that decreasing much more significantly. Okay. So if my base is less than 1, I have a decay. Okay, so here we have some general growth and decay functions drawn out. Anytime we're increasing, we see this curvature going up, we have growth. Anytime we're decreasing, we have decay. Now, a lot of times, the actual practical applications of these growth and decay functions involve this value e. Okay, e is called the natural number. It is a value that we see that occurs a lot in nature. It also occurs with some of our growth with finances. So we'll see it repeat periodically as we're working through different functions. But we can see that any function that's written in the form a times b to the x can also be written as a times e to the kx. Okay? Using that e value and allowing for that e value to be in there is really helpful. It actually has more applications ultimately. And that's why we're going to look at that a little bit. We'll see this e, and it's going to keep coming up. E is going to come along a lot. Let's take a peek just really quickly at where e is on your calculator and what e's value is. Okay? For whatever reason, we actually have 2 locations for e. It's a little hard to see on the screen here, so you have to look on your own calculator. But above the ln key, natural log, is e to a power. Above division is e. Either one of those works. You just have to put your own exponent if you use the plain e. If you want to use the e above the natural log and have it automatically be prepared to have an exponent, that would be fine too. Okay, they're both the same value. If I just want to find e, helps if I turn it on, we're going to hit second divided. We just want to know what the value of e is. If we hit enter, we see our value of e. E is like pi. It has a set value. Okay, it is infinitely long as far as we know. It's irrational. So 2.718 is a good approximation for it, 2.72. I usually tend to use 2.718, just like we have our pi 3.14. If you remember any more of it, it's 159. Okay, we have our value for e. So get comfortable with that idea of e. All right, so we're going to look at determining if we have a growth or decay, whether there's e in there or not. Okay, e is 2.718, so it's larger than 1, so I have e to the x. E, the base being larger than 1, this is a growth function. Here, we have f of x is 2 to the negative 5x. Recall, for determining the base, it needs to be just the plain old x. So it's really 2 to the negative 5th to the x. Okay, 2 to the negative 5th, that's a small value. That's 1 over 32 to the x. So we have a decay, because our base is less than 1. How about here, 0.25 to the negative x? Well, we need to figure out what that is to the x. So really I have 0.25, which I'm going to change to a fraction. I like to work with fractions more. I know you don't all like that, but 0.14 or 1/4 to the negative x, or to the negative 1 to the x. That gives me my negative x. So now I have 1/4 to the negative 1. That means I have the reciprocal, or 1 to the negative 1, 4 to the negative 1. That actually is technically 4 to the x. Okay, 1/4 to the negative 1 is a reciprocal, flips it over. And so we have growth. Okay. All right, for time's sake, I'm going to pause the video here and you can go on to the next one.